Okay, welcome to the lecture 13. So in lecture 13 we'll discuss the Lagrangian for a free particle. The most simple possible system is a free particle, maybe in one dimension. So we will see what will be the structure of Lagrangian. So before we begin the lecture 13, let me recap of previous lectures. So this is a online class, and we cannot see the reaction of the students. So I am not able to see how much you are understanding, how much you are getting what I am teaching in this online class. So please feel free to raise your concern in the discussion forum, which will look every day and try to address your questions. So let me recap the past few lectures. So what we have done, we have considered principle of virtual work, and there we obtain the D'Alembert's principle. So D'Alembert's equation, which is the ddt of del t del qi dot minus del t del qi equal to qi. The T, capital T, is the total kinetic energy of the system, and Q, capital Q, is the generalized force, I equal to 1 to S number of degrees of freedom. Then we consider the Hamilton's principle, which is also known as principle of least action. Okay, principle of least action. It has two parts. I repeatedly mentioned. First part introduce Lagrangian. Of Lagrangian, and second part says that classical system will follow the path for which the delta S will be 0, that x will be extremum, where S is the action of the system, which is line integral of initial point to final point, right. So system will evolve from the initial part to the initial state to the final state in such a way that axiom should be extremum. So this Hamilton principle, and using Hamilton's principle we found that Euler-Lagrangian equation which says ddt of del L del qi dot minus del L del qi equal to 0. So two different ways we have found, and they are very similar, and the one equation is D'Alembert's equation, another equation is the Euler-Lagrange equation, and they are very similar. So there are similarity and differences we will discuss later once we find the structure of Lagrangian. So then in the very last class, that lecture 12, so in lecture 12 we discuss the properties of the Lagrangian. So what are the properties? That Lagrangian is always, you can multiply with the constant. In the Lagrangian you can add some constant without affecting the equation of motion. then you can have Lagrangian, you can construct of a combined system. So if you have two isolated system, the Lagrangian of system A plus Lagrangian of system B will give you the combined Lagrangian. If the systems interact among themselves, then you can find the Lagrangian of first system plus Lagrangian of the second system plus the Lagrangian of the interaction. So in this way you can find a Lagrangian of system. Then fourth properties we have learned is that cyclic coordinate. If a Lagrangian does not depend on a particular generalized coordinate, then it is called cyclic coordinate. And we have seen that it is very important to find a cyclic coordinate, because for each cyclic coordinate we can always find a conserved quantity. So if qk is cyclic, then pk, the momentum conjugate to qk defined by del L del qk dot is conserved. So one conserved quantity is associated with every cyclic coordinate. So it is very important to find cyclic coordinate, and that will automatically give you the conserved quantity, one conserved quantity. And I also mentioned, but have not discussed, that the presence of a cyclic coordinate indicates that there is certain symmetry in the theory, that we will understand more when we discuss the symmetries and conservation laws. Okay. Then the last properties was the most important properties, that if a Lagrangian is differed by a total time derivative of coordinate, generalized coordinate and time, then it describes the same system. L prime and L will describe the same system. So a Lagrangian, we can in any Lagrangian we can add a total derivative term, we can subtract a total derivative term without affecting the dynamics of the system. So a Lagrangian can be added with a constant term, a Lagrangian can be multiplied by a constant term, a Lagrangian can be added with the total derivative of generalized coordinate and time, total derivative of a function of generalized coordinate and time without affecting the dynamics of the system. And this is very important, we will see in the context of gauge transformation, we will discuss when we discuss the motion of charged particle in the electromagnetic field, and it is also very important, this transformation, in context of canonical transformation when we discuss canonical transformation. Okay, so these are all the part of my previous lectures. So if you have queries, questions, please raise in the discussion forum, and we'll address this. Now in this lecture 13, we'll study the Lagrangian for a free particle. Okay, so let us consider a free particle which is described by its, say, position r and its velocity v and time t. So this can be the general form, general structure of a particle, okay, whose position vector is r, velocity is v and time is t. Okay. So now what will be the Lagrangian of a free particle? That is our plan to look at. Now for a free particle, we know that free particle, if it is moving, then it will continue moving in the straight line forever, right? This is for, so such motion we can find that space is homogeneous. I'll explain the meaning. Space is homogeneous for a free particle. That means if you shift your coordinate, if you shift your origin from, say, 0 to any arbitrary value, then it will not be affected. Meaning is that a particle, free particle, will move in a straight line, and if there is no force, external force disturb it, it continue its motion in the straight line. So that means it does not depend, this dynamics does not depend whether you are choosing your origin at 0 0 or you choose your origin at somewhere else. So this is called the space is homogeneous for free particle. So this indicate that this Lagrangian for a free particle cannot depend on the position. So delta del L del R should be 0 for free particle. Okay. Second thing is that exactly similar way we can say that time is also homogeneous. Particle. I will explain the meaning of this time is homogeneous. A free particle is moving in a straight line. So whether you looking at that particle at 10 o'clock or 11 o'clock or 12 o'clock, you will find the same dynamics. It is moving with a constant velocity, constant speed in a same direction. So time is also homogeneous for a free particle. So for a free particle, Lagrangian cannot depend explicitly on time also. So del R 0, del L del T is also 0. So if we combine these two quantity, then we find that Lagrangian for a free particle is function of only v, velocity. So for a free particle, space is homogeneous, time is homogeneous. So Lagrangian cannot depend on space and time explicitly. So the dependence of R and T is ruled out. So Lagrangian should be function of v. Now for a free particle, the space is also isotropic. That is, the Lagrangian, that dynamics of the system will not be affected in the rotation of the coordinate. So if you rotate your coordinate system, free particle will continue moving in the same direction as it was moving previously. So rotational invariance implies that Lagrangian, now which is depend only on velocity, cannot depend on the direction, rotational invariance. So with these three properties, the space should be homogeneous, time is homogeneous, there should be translational invariant, and space is also isotropic. So Lagrangian for a free particle is only depends on the magnitude of the velocity. So magnitude of velocity, that is v. So now for a free particle, Lagrangian depends on v square. Okay. So I prefer to write instead of mod v dependence, Lagrangian depends only on v square. So no directional dependence in this case. Okay. Now let us consider two inertial frame, and we will look at the Lagrangian at the different system. So suppose I have the frame S, say let us assume this is fixed, and another frame S prime which is moving in the x direction with a small velocity epsilon. Direction. So S prime frame is moving with respect to S, which is stationary with a small velocity in the x direction. The velocity is epsilon. So now the observer in the S frame will see a Lagrangian which is for the free particle, it will be L v square. The observer at S prime frame will see that it is a v prime square in his or her frame. Okay. So but this v prime will be the v plus epsilon. So in the, but these are the inertial frame, both are inertial frame, and physics is not supposed to change in this frame. So all laws of motion should be covariant in all inertial frame. Okay. So L prime v prime square I minus L v square I can calculate and we can see. So if we expand L prime v prime square, which is L prime v plus epsilon square, then it is L prime v square plus 2 epsilon dot v, right, and I am neglecting the epsilon square term because I already said epsilon is very small velocity. Okay. So I am neglecting. So this is L prime function of v square plus 2 epsilon dot v. Now if I expand this in Taylor series, I can expand this in Taylor series. So we will have L prime v square plus 2 epsilon dot v del L prime del v square. Okay. And a higher order term in epsilon square, which we are neglecting. So L v prime minus L, you can write to v dot or epsilon v dot epsilon times del L prime del v square. So the difference of these two Lagrangian, because now these are two inertial frame, so they should describe the same system. So I am now considering the difference of two the Lagrangian in the two different frames, and that we found this can be written as 2 v dot epsilon times del L del v times v square, because my this term is already multiplied by a infinitesimally small epsilon. So v L prime can be replaced by L, otherwise the additional terms will be the higher order in epsilon. Okay. So now under which condition, now we have to look under which condition L prime v square and L v will describe the same dynamics as we need for that both are the S and S prime are the inertial frame. So look for a solution that okay. So first is that if you have L is constant, suppose I find L is constant, or suppose del L del v square is 0. Suppose we consider this solution that del L del v square is 0, that means L is constant. So in that case I find L v prime square is same as L v square. So Lagrangian in the two frame is same, but this is the trivial solution. So this is trivial. Lagrangian is constant, no dynamics. So this is trivial solution, because Lagrangian is constant. Lagrangian constant means no dynamics. Okay. So this solution is not interesting and ruled out. So this is not an interesting solution. Now second next possibility we look for, next possibility we can look for is that, let us say del L del V square is constant. Suppose del L del V square is constant, then what will happen? Then L prime V square minus L V square will be 2 epsilon dot V times some constant. Okay. So this means this I can write as ddt of 2 C r epsilon dot r, right? Epsilon is constant, C is constant, so derivative r will give you the V. So V is, because V is dr dt. Okay. So we find the difference of two Lagrangian in the two different system is nothing but L prime V square V prime square minus L of V square is ddt of some f, which is function of coordinate r, generalized coordinate r. So now recall the properties, the last properties, fifth properties, that if two Lagrangian is differ by a total time derivative, if two Lagrangian are differ by a total time derivative, then we have that the Lagrangians, then we have the same dynamics. Okay. So this is the solution we are looking for. So our Lagrangian, because S and S prime are inertial frame, so they should describe the same dynamics, and from that condition we find that del L del V square should be constant. That means L should be C V square, and I am not adding some constant term, because adding a constant term to the Lagrangian does not imply anything, right? It will not affect the dynamics. So Lagrangian should be for a free particle of C times V square. Now suppose if it is C times V square, then what kind of equation of motion it describes? So let us see that what kind of equation of motion. So let us find equation of motion for the system. Okay. So we already know Euler-Lagrangian equation. So let us use the Euler-Lagrange equation, that ddt del L del V. Here I am, instead of q dot I am writing V, and then del L del R will be 0. So this will be the equation of motion. But Lagrangian is simply C times V square, so it does not depend. So this is 0 for this Lagrangian. So we have 2 C V dot equal to 0. That means 2 C R double dot equal to 0. So this is the equation of motion we obtain from the Lagrangian. V square, which we claim suppose to be the equation of motion for a free particle. But we know the equation motion for a free particle. The equation of motion for a free particle is m r double dot equal to 0, force acting, because there is no force acting. So, m double dot equal to 0. So, from here we can see that if we choose our C in the Lagrangian, so if we choose C equal to m by 2, where m is the mass of the particle, if we choose C equal to m by 2, where m is the mass of the particle, okay, then we obtain the Lagrangian L equal to m by 2 v square or half m v square, which is nothing but the kinetic energy of the particle. So, we come to this conclusion that Lagrangian for a free particle is nothing but the kinetic energy of the particle. The kinetic energy of the particle. Okay. So, we arrived at a very important result, that Lagrangian of a particle, free particle, is nothing but the kinetic energy of the particle. So, what about the particle which is not free? So, if the particle is not free, what will be the structure of the Lagrangian? So, suppose we consider a conservative system. A conservative system, the force can be written as del u del, say del r. So, if you have the r is the coordinate, then we can write for a conservative system, we can write this force is this, and the equation motion for a particle having a force F will be m r double dot will be F, which will be m r double dot equal to minus del u del r for a conservative system. Okay. Now, if we just write our Lagrangian, which is half m v square r dot square and minus the potential energy r, and find the equation of motion, it will lead to m r dot minus del u. This point will elaborate in my next lecture. So, this time is over for this lecture. So, let me tell you that in this lecture 13, we have seen what will be the structure of the Lagrangian for a free particle, that we said that it is kinetic energy of that particle will be Lagrangian. And then now we are going to see that for a particle which is not free, Lagrangian will be like t minus u. That point will emphasize in next lecture. Okay. So, thank you.